Hello everyone, this is my video about using Sage to solve some of the most difficult problems that we had in this chapter, and there will be an opportunity to use Sage. I actually think that I will decide for having a non-Sage portion and Sage portion of the test, since we can extend the time a little bit. In any case, this is the problem. I hope you can see it on your screen now, and this is definitely on the easy side. With or without Sage, you should be able to do it quickly. So absolute, local, extreme points, and inflection points. So I started my code for a tiny bit. I typed it up. Let me make sure it runs as intended. And remember, whenever you want to make a comment, and maybe you do want to make a comment, you can do it starting with a sharp symbol. And also you can define a function and define a derivative. And after it has taken the derivative, look at it and make sure that so far so good. So there is no problem knowing the derivative of this thing. There shouldn't be any. So definitely check on every step whether what you are getting is somehow realistic or not. Okay, so this looks fine to me. So I'm gonna go on and solve an inequality. So when is this positive? When is the derivative positive or negative? So solve. Actually, I might call my solve df bigger than 0. df bigger than 0. And I'm solving with respect to x. I think this should be fine. Let's try. It should solve just fine, since this is purely an polynomial equation. I don't know why it takes a while, so I'm waiting and waiting. Here we go. So it is bigger than 0 when x is bigger than 0, or x is less than 2. So I can make it into a comment. So derivative positive on interval from 0 to 2. And that means that the function is increasing on that interval and is decreasing elsewhere. So this is a first derivative test used, and hence we actually know what's happening. And let me pause the video and type up some stuff so that it's easier for you to follow. All right, so my function is decreasing from -infinity to 0, then increasing on 0 too. So at 0, it has at least a local minimum. At, say, x equals 0, a local minimum, and I can show it as 0 f of 0. Well, let's hope it worked like this. 0, 6. Okay, I don't know why it did. Maybe it's easier to do print. You can also do print. That's just a Python thing. 0 minus 6. Okay, either way, we have a local minimum at 0, minus 6, at the point with y value minus 6. And very similarly, again, you don't have to use the same field, the same cell. You can add as many cells as you want. Similarly at 2, figure out what's going on at 2. I'll copy paste most of it. Be careful with copy pasting. That is definitely a way to introduce an error or a typo. So here we have 2 minus 2, and that is a local maximum because it was increasing on the left, decreasing on the right. Look at the first derivative test, or where it talks about positive derivative and negative derivative, or just use your common sense. The function was continuous everywhere. It was increasing up to 2 and then it was decreasing. So this is a local max. Well, at the point with y-coordinate -2 and x-coordinate 2, what about absolute extreme points? Well, we have an unbounded domain. That implies that we need to check infinity. And, well, kind of obviously at minus infinity, the value is plus infinity. And how do we know that? Let's remember limit f infinity. I think that's how it works. Maybe I need an x here, but we'll figure it out momentarily. Whoops. Expression, oh, okay, equality. When x goes to infinity, the f value is going to minus infinity, and you can realize really quickly that it does, and for that, all you need is, oops, I introduced something wrong in here, undo. Let me stop this. I was too happy to use a mouse, so okay, now it's back to normal. All right, so we have minimums, maximums, and when x goes to infinity, the value of the function goes to minus infinity, and very similarly, we can check that when x goes to minus infinity, the value of the function goes to plus infinity. So hence, there is no absolute minimum or absolute maximum. All right, we're done with this problem. This is the whole code for it, and I'll see you in the next one.